All right, so let's look at something called linear programming, and we'll explore it through an example. Um, Linear programming is maximizing or minimizing, namely optimizing, some sort of profit or some cost or something like that based on some limitations which occurs all the time in real life. So can be really complex problems that you try to solve, but if you can boil them down to linear equations, linear inequalities, then you can solve it using what we've learned about optimizing an objective function. So this example we're going to do is a pretty lengthy paragraph. So I'm going to type that out, and if you're taking notes, I recommend, of course, that you write it out as well. And I'll try to go slowly here, and we can sort of think about what the problem is describing as we type it up. So it starts with a farmer has 70 acres of land available. Farmer has 70 acres of land available for planting soybeans and wheat. Okay, so we can see that we already have a limitation, right? There's only so much land we can use, so that'll come into play later. The cost of preparing the soil, the workdays required, and the expected profit per acre planted for each type of crop are given in the following table. So this problem is very nice because we're going to have a table to describe certain aspects of the problem. Oftentimes that won't be the case. So this is kind of an introductory example here. So let's insert our table. I need 4 rows and 3 columns. Okay, and so we're going to have the preparation cost per acre. We're going to have the work days required per acre. And again, the reason I'm typing all this out in the video is in case you're taking notes, you can kind of write it up with me as you go. Then we've got the profit per acre. Okay, and we need to list these for both soybeans and wheat. Alright, so for soybeans, we're looking at $60 of preparation cost per acre, and for wheat, we're looking at $30 of preparation cost per acre. The workdays required per acre are 3 and 4, and then the profit per acre is $180 and $100. Okay, so this is describes sort of some limitations on, or actually requirements needed per acre for soybeans and for wheat, both having different requirements. All right, so let's continue. The farmer cannot spend more than $1,800 in preparation. Okay, so he's limited to $1,800 in the preparation cost per acre. He is also limited to a total of 120 workdays. So you can imagine there are man hours that are needed to work the land, and so with his employees, he's limited to a total of 120 workdays. How many acres of each crop should be planted to maximize the profit? Okay, right, that would probably be the ultimate goal here, is to maximize the profit. Okay, so that's the problem we are trying to solve. So let's get to it and sort of identify what process we want to use in order to solve this problem. Okay, so where do we even start? There's so much going on in this problem. So the first thing is with optimizing an objective function, we need to identify the variables. So we need to, we're dealing with two variable linear inequalities. So we need to identify an x and a y. And they need to be numbers. So we need to say something like, let x represent number of, and we'll fill in the blank. And we also need to say let y represent number of. It's important to say explicitly what these represent. This is the first thing that students skip, and it really gets them into trouble. So don't skip this part, okay? All right, so if we look at the question says how many acres? How many acres of each crop, right? So that's what our variables are going to tell us. So what might x represent? Well, x could represent the number of acres of soybeans. And then, of course, then y would be the number of acres of wheat. Okay? So we have to kind of search through the problem to find out what the two unknowns are, and then those will be our x and y. Okay? Now, what is the second thing that we do? So second, and this is consistent sort of procedure for every linear programming problem. Okay? So the next thing we need to do is identify the objective function. And the way to recognize an objective function when it's in this sort of paragraph form is, again, and write these side notes down. Okay, I'm not writing everything down here. I'm explaining it. If you're taking notes, make sure to write your side notes. So when you want to identify the objective function, you read the question and you're looking for the item that you're trying to maximize or minimize. The objective function is always what you maximize or minimize. So in this problem, when we read it, we're looking to maximize profit. We're looking to maximize profit. Okay? So in this case, the objective function, we might use P for profit. And so we have to read through the problem and discover a formula for calculating how much profit. Well, luckily for us, in this table it tells us right here how much profit we will make for each acre of soybeans and each acre of wheat. Okay? So when we look at this, the profit will be based on X acres of soybeans and Y acres of wheat. So when we set this up, if we have X acres of soybeans, how much profit will the soybeans give us? Well, the soybeans will give us $180 for every acre of soybeans, and we have X of them. So we multiply 180 times X to calculate the soybean profit. But we also have Y acres of wheat at $100 per acre. So we need to add 100 times Y to get the profit for the wheat. So 180x is the profit for soybeans, and the 100y is the profit for wheat. We need to add those together to get our objective function. So that's what we're trying to maximize in this case. Okay. Now, the hardest part, in my opinion, of these linear programming parts are finding the constraints. Okay. So the constraints are the limitations of the problem. So we have to start at the beginning and sort of read through. So I will highlight limitations in blue. Okay. So a farmer has 70 acres of land available. So right there, that's a limitation. We only have 70 acres total. So let's come down here and sort of, well, you know what, let's identify the limitations first, then we'll write the inequalities. So 70 acres total. We can have less than that, but we can't have more than that. Okay. All right. Preparation cost per acre. These aren't limitations. These are just facts. Okay. But then we read on. The farmer cannot spend more than $1,800 in preparation. So we have to spend $1,800 or less in preparation based on these numbers. Okay. And he also is limited to a total of 120 workdays. So we can have 120 workdays or less. So we have our three limitations listed. Okay, so the first thing we have is a limitation on the amount of land. The total land, the total number of acres, has to be less than or equal to 70. Less than or equal to 70. Well, how much land is there if we have X acres of soybeans and Y acres of wheat? We always go back to these X and Y values, these X and Y variables. So we know that X plus Y, the number of acres plus the number of soybean, the acres of soybeans plus the acres of wheat have to be less than 70. So that's one of our constraints. Okay. Then we have a preparation limitation. Preparation. The total preparation cost has to be less than or equal to 1,800. We can't exceed that. So how do we calculate how many preparation how do we calculate preparation cost? Well, luckily it's in a table format. And if we have $60 of preparation cost per acre of soybeans, and we have X acres. So that's 60 times X for the cost of preparation per acre of soybean. Plus, similarly, 30 times Y for the preparation cost of wheat. And that, when we add that together, that needs to be less than or equal to 1,800. Now, we know where we're going to go with the algebra here. So what I recommend, you know what, we'll come back to that. Let's come back to that. All right, so we've got a limitation on land, a limitation on preparation. We have a limitation on work days. We have to be less than or equal to 120 total work days. And we'll move a little quicker now. We've got 3 work days per acre of soybeans, and we've got X acres of soybeans. So the number of work days for soybeans is 3 times X, and the number of acres for wheat is 4 times Y, right? 4 work days per acre of wheat. And we add those together, and that has to be less than 120 total. So those are our 3 limitations. Now, let's write them as a system. Now, as a system, we have to sort of incorporate 2 other limitations that aren't explicitly stated. Since X is a number of acres of soybeans, X cannot be a negative number of acres. It could be 0 acres, but it can't be negative. So X has to be greater than or equal to 0, and similarly, Y has to be greater than or equal to 0. Those 2 constraints are typically listed depending on the problem. You often can't have negative numbers in real-world applications. There are cases where you could lose money, for example, and you could have negative values, so you wouldn't have these constraints. But in this case, we can't have negative acres, so those constraints are sort of implied. Now we list the other 3. X plus Y is less than or equal to 70, and now I can see that this inequality for preparation, all terms here are divisible by 30, so I'm going to divide both sides by 30 to make this a little easier to work with. So that's going to give me 2x plus y is less than or equal to 60. And then last we have 3x plus 4y is less than or equal to 120. So those are the constraints that we're working in. And we need to maximize our profit function based on these constraints, okay? So now we're going to get down to the optimization part. So what we need to do is graph our constraints, find the vertices, and plug the vertices into the profit function to see which one yields the maximum profit, okay? So to do this, all 3 of these inequalities here are in standard form. So to graph those, I think the intercepts are going to be easiest. So in this inequality, if we think about the boundary line, if we plug in 0 for x, then y would have to be 70. And I'm not going through all the details of this. Work it out on your own if you need to, but these are pretty simple to find the intercepts. And then if we plug in 0 for y, then x would have to be 70. Okay? And if you use a test point 0, 0, 0 plus 0 is less than or equal to 0. So we need to shade, since that's true, we need to shade the 0, 0 side. Okay? So now we know everything we need to know about graphing that. Okay, then we've got 2x plus y is less than or equal to 60. So if we plug in 0 for x, y would be 60. If we plug in 0 for y, then 2 times x would equal 60, so x would be 30. If we plug in 0, 0, 0 plus 0 is less than or equal to 60, so we will shade the 0, 0 side, again, of this boundary line. Alright, one more time. If we plug in 0 for x, we get 4y equals 120, and divide both sides by 4, we can see that y is 30. If we plug in 0 for y, 3 times x equals 120, so x has to be 40. And if we plug in 0, 0, that's true, so we again shade the 0, 0 side. Alright, and I didn't make any, I guess we could say on this guy, x is greater than or equal to 0, so we'll shade to the right. We don't have to use the test point. And if we look at y is greater than or equal to 0, that means we'll shade above that boundary line, if we wanted to list something there too. Okay, so let's get down to graphing all of this. And we're looking when x is greater than or equal to 0 and y is greater than or equal to 0. So we're going to look at the first quadrant only here. And we can see, given all of the ordered pairs, 30, 40, 60, 70, let's go by tens, okay? Let's go by tens. So that's 10, so this will be 20, 30, 40, 50, 60, 70. That's about as big as we get. So 10, 20, 30, 40, 50, 60, and 70 is there. Okay, so let's graph each of these. X is greater than or equal to 0. Well, that's this vertical boundary line on the y-axis. That's our first boundary line, and we need to shade to the right. So we're looking at everything to the right of that line. Y equals 0, that boundary line is the x-axis, and for that guy we need to shade above. So now we can see that we're limited to just this first quadrant, okay? Then we've got x plus y equals 70, so that goes through 0, 70, and 70, 0. So we've got this boundary line. So that's the boundary line, x plus y equals 70, and we need to shade the 0, 0 side. So now we have the first quadrant, but now we've got to shade the 0, 0 side of this line, so we're limited to this triangle. Just kind of keeping track of our feasible region as we work this. The next line goes through 0, 60, and 30, 0. Okay, so that is 2x plus y equals 60, and we'll also shade the 0, 0 side. So now we're limited just to this triangle, right? Because everything on the other side is not on the 0, 0 side. So it turns out that this x plus y equals 70 boundary line is not going to do anything for us in this problem. It's the land limitation. Remember, we had 70 acres. That's really not going to be a limitation for us because other things are going to limit us even more. All right, our last boundary line is 3x plus 4y equals 120. It goes through 0, 30, and 40, 0. Okay, and so that's 3x plus 4y equals 120, and we need to shade the 0, 0 side. So now we're limited to this quadrilateral. That's our feasible region right there, which has 4 vertices. Okay, so these 3 vertices on the axes, those are very simple. So let's list those vertices. We have 0, 0. We have 0, 30. We have 30, 0. And this last one is not obvious. So this last one is where this line intersects this line. So in other words, it's where 2x plus y equals 60 intersects 3x plus 4y equals 120. I apologize for my voice here. So we need to find the intersection of those two lines. So we'll solve the system of those two equations. So we've got 2x plus y equals 60 and 3x plus 4y equals 120. So I'm going to solve this by elimination. So what I'll do is I'll multiply the first equation on both sides by -4, because that's going to give me a -4y, which will cancel with my positive 4y. So I get -8x minus 4y equals -240, and 3x plus 4y equals 120 doesn't change, and I'll add those together. So the y's cancel, leaving -5x equals -120. And if I divide both sides by -5, I get x equals 24, which seems reasonable that this x value would be 24. Now to get y, I'll plug 24 back into one of these equations. So I'll plug it into 2x plus y equals 60. So I get 2 times 24 is 48, plus y equals 60. And if I subtract the 48, I can see that y is 12. So our last vertex is the ordered pair 24, 12, which seems reasonable. This looks like it could be 12 if I graphed it precisely. So there are the vertices. So now, to optimize our objective function, I need to plug those 4 vertices into the objective function, the profit function. And the profit function, remember, let's write it out again. The profit function was 180x, p equals 180x plus 100y. So if I plug 0, 0 into that, I can see that p equals 180 times 0 plus 100 times 0. So that means, remember what x is. X is the acres of soybean and y is the acres of wheat. So that means if I have 0 acres of each, then I'm going to profit 0. That makes perfect sense. If I have 0 acres of soybeans and 30 acres of wheat, then my profit will be $3,000. If I have 30 acres of soybean and 0 acres of wheat, then my profit will be $5,400. And finally, if I have 24 acres of soybean and 12 acres of wheat, then my profit, let's see, my profit will be 5,520. Okay, so that's my maximum profit. So the maximum profit is $5,520, and $5,520, and we would have to, let's say, $5,520 with 24 acres of soybeans and 12 acres of wheat. So now this farmer knows exactly how many acres of each to use, and he doesn't exceed any of his constraints. For example, he only had 70 acres total, and here he's only using 36 of those acres, so he doesn't exceed that. You can check that his preparation cost will not exceed his limitation. His work days will not exceed his limitations with these numbers, and he will earn his maximum profit in this case. So these problems are very lengthy. The hardest part is setting them up. Once you get them set up, once you've identified your variables, your objective function, and your constraints, the graphing and finding the vertices. For example, you have to shade your feasible region, because you might think that these are vertices, but they're not. They're not corners of your feasible region. We're only interested in the vertices of the feasible region to optimize the objective function. So be careful with that part of the algebra. But otherwise, the algebra is pretty simple. The hard part is identifying your objective function, formula and your constraints formulas. So practice, practice, practice.